Welcome to MEI Mechanics. We're on the topic of impulse and momentum 2, collisions in 1D, and this is video 2.1, Newton's law of restitution. Now, whenever we've got a direct collision between two objects, we're going to assume that there are no other forces acting, so we're just going to be thinking about the momentum of the two particles both before and after the collision, and that momentum, as we've seen previously, is going to be conserved, and that depends just on the masses and the velocities of those particles. But there is another thing to consider. We've seen at least one example where we've been told that two objects coalesce, so they form just one object and move together after the collision, and other examples where they don't. So there seems to be some freedom here in terms of what happens after a collision. So you can conserve momentum, but that's not the whole story. There are lots of possible pairs of values for the two final velocities that would give you the same total momentum. And so the missing piece of the puzzle actually is energy, and that's the energy which is lost in the collision. Depends on the elasticity of the objects, and that can be found by experiment and forms what's called an experimental law. Now, in terms of what this has to do with energy, we will talk about that more in later videos, but just very briefly, if a collision is said to be completely elastic, then that's where no energy is lost, and if there is energy lost, then it's inelastic. And so the extent to which energy is lost, in a sense, is what we mean by this idea of restitution. So it's a measure of how elastic the collision is, with fully elastic collision being one in which no energy is lost. The amount of restitution that we have depends on the two materials that make up the objects. Now, the thing we use to measure restitution is called the coefficient of restitution. That's given the letter E. And that's defined by Newton's law of restitution as the separation speed divided by the approach speed. Now, what we're going to assume, and this is what has been found to be true in most of the time with experiments, is that this thing is a constant for any two objects. So it doesn't matter how fast they approach each other, that ratio will still be the same. Now, in reality, that might not be true in every case, but that is a very good model for most situations. Now, if you think about it, it would be very odd for the speed of separation to be greater than the speed of approach. That would mean that we'd gained energy from somewhere, and that can't be possible. So we know that this thing has to be less than or equal to 1. It is possible, however, for this thing to equal 0, and that's where the separation speed is 0. So that's when we're talking about objects sticking together or coalescing, then they're not separating, and so the separation speed is 0. So this value E can be anything between 0 and 1, with 1 being perfectly elastic. So here's an example then. So we've got two objects moving towards each other. So one of them's moving at 5 meters per second, and the other one's moving in the other direction at 2 meters per second. And then after the collision, the one that's moving at 1 meter per second, and the other at 4 meters per second. And we're just going to see if we can calculate the coefficient of restitution for this combination of materials. So we need the separation speed. Now, because they're moving in opposite directions, that those two things are going to add together. So if that moves 1 meter that way, while that moves 4 meters that way, then they've separated by 5 meters, and that's happened within 1 second. So we add those together. So that's 1 plus 4, and likewise for the approach speed. If that moves towards that object by 5 meters and that moves towards that object by 2 meters, then they've got closer by 7 meters in that time. So again, we're adding those together. So that is 5/7. So, asking a question in a slightly different way this time. This is more about predicting in some way what's going to happen, at least to one of these objects. Before the collision, they're moving with speeds of 6 meters per second and 2 meters per second, and we're told that the coefficient of restitution between these two objects is 3/4. So this value of e we know to be equal to 3/4. Now the separation speed we don't know, but what we do know is that those things are both, at least in terms of how we've drawn the arrows, moving in the same direction. Okay, so if that's moving at v meters per second to the right, and that's moving at 4 meters per second to the right, I'm going to need to look at the difference between that 4 meters per second and that v meters per second to find how quickly they are separating from each other. If, however, it turns out that v is a negative number, then we'll interpret that as it actually moving to the left. So we need to be really careful with our signs in this topic. The approach speed will be 6 plus 2. And what we know is that that is equal to the coefficient of restitution, which is e, and we're told that is equal to 3/4. Alright, so if we rearrange that for v, we find that v is minus 2 meters per second. In other words, this object, even though we've drawn an arrow to the right, we now know that that is a negative number, and so if we were doing it now, redrawing the arrow, we're going to the left with a value of 2 meters per second, because it's travelling 2 meters per second to the left. So the thing to realise about these problems is that we don't know beforehand what direction. We don't know whether that object is going to be moving to the right or to the left after the collision. We know it's going to be separating from the other object, but it can still be getting further away from the other object, even though they're both going in the same direction. It's just that other object is going to be going faster. So conceptually, this topic can be tricky at first. You've got to imagine these things moving towards each other at different speeds, maybe both even moving in the same direction beforehand, just at different speeds. As long as they're getting closer towards each other and then moving away from each other afterwards, then you can have a collision that you can analyse. In an example, we're really going to see the power of this method. Because notice at this time we're told everything about what's happening beforehand, and we're told the masses of the objects and the coefficient of restitution, but we're not told the velocities of either of the objects afterwards. So why don't we call the final velocity of this object v1, and we'll call the final velocity of this object v2. So from Newton's law of restitution, we can say this: the speed of separation, which will be v2 minus v1, you might want to convince yourself that that will have to be a positive number, because that, if they're separating, then that has to be greater in that direction than that one. Divided by the speed of approach, which we can see is, well, we've got 4 in that direction, 6 in that direction, so that's a speed of approach of 10. And that equals 2/5. Okay, so there's not enough information there yet to work out what either of these things are. But we have some extra information that we've not used there, and that is the masses of these objects. Now what does that allow us to do? Well, that allows us to work out the total momentum, which is 4 times 4 for this object, 4 kilograms and 4 meters per second to the right. And because this one's moving to the left, this one has a momentum of 3 times minus 6. Work that out, that's minus 2 Newton seconds. Now that's the total momentum, and the total momentum is conserved. Doesn't matter what the coefficient of restitution is, That tells us something about the energy, as we'll see in a later video, but the momentum has to be conserved. So what that means is that we can say something else about V1 and V2, and that is that 4, that's the mass of that object, times V1, so that's the momentum of the first object, plus 3 times V2, which is the momentum of that second object, that will still be minus 2 after the collision. So now what we have is a pair of simultaneous equations. So if we solve those simultaneously, then we can work out separately what V1 and V2 are. So by doing that, and I'll trust that you have enough experience of algebra to check this for yourself if you want to, V1 is minus 2 meters per second. So that means it's travelling 2 meters per second to the left. So this object has actually changed direction. And V2 turns out to be 2 meters per second. So that is travelling to the right, as we'd probably expect. So that concludes video 2.1 on Newton's law of restitution. The next video will be 2.2, loss of energy due to impact.